All right, shall we get started? So today we'll be using all those equations we derived and applying it to specific scenarios and try to get an understanding about how these macroscopic properties change. Like what is your internal energy change or enthalpy change for a specific thermodynamic process. So before I get started, I just want to quickly emphasize some of the concepts that people might be confused about. So let's look at our first law of thermodynamics, which you have du equals to dq plus dw. All right, so a common mistake people make is write this one as like delta U equals to delta Q plus delta W. So this one is just not correct. Like, do not do that. And the reason behind it is if we're taking the integral on both ends of this equation, what we have is du integral equals to integral of dq plus integral dw. Now, on the left-hand side here, our internal energy is a state function. So recall when we were saying it is a state function, it means it doesn't matter what path you take for this integral to complete. So this one you can rewrite as u2 minus u1, or you can write it as delta u, because u is a state function. All right, but on the right-hand side, that is a different story. Your heat and work are both line functions. So your Q and W here are line integrals. So their integral actually depends on what kind of path you're taking. So just using the basic concept of integral, let's take work as an example. Well, we're talking about PV work, right? You have P and you have V. Now, from your initial point to your final point, so depending on what kind of path you take, like the red path here, its work you can find by taking the area below that red curve. All right? And likewise, if we have a blue path, now the work will be the area below that blue curve. So it is a line integral, or how do we take that integral? It depends on what path we're taking. So taking together, what we do if we take integral on both ends of this equation, we end up having delta U equals to Q plus W. So we'll not write something like delta Q or delta W because that's a pretty ill-defined term, given the nature of Q and W are line integrals. Just keep that in mind, all right? Okay, and that's a bit of the review on the first law of thermodynamics. And today we will be using first law of thermodynamics and also some of the definitions that we have, for example, definition of enthalpy, definition of your heat capacities, and also the properties of your ideal gases to work out some of the relationships for ideal gases. So let's get started. So your textbook did introduce the new terminology of perfect gas. By say a perfect gas, you have delta U partial derivative of U over V at constant T equals to 0. Effectively, perfect gas and ideal gas are the same thing. It has a proof of that coming from statistical mechanics, but we probably won't go over it. I'm just following the notation of your textbook, so you are not lost. But in fact, the ideal gas and perfect gas, they are the same thing. All right. Okay, so when we're talking about perfect gas or ideal gas, in here, we have several things we want to keep in mind. First of all, for ideal gases, whenever you see ideal gas in your problem, you should instantaneously write out the ideal gas law. Remember, that's an equation of state that tells you the relationship between your macroscopic properties like pressure, volume, temperature, and number of moles. And for ideal gases, we also have some additional properties. For example, your internal energy is independent from its volume. Or the other way to put it is your internal energy of an ideal gas is only a function of T. And likewise, your enthalpy of an ideal gas is also only a function of T. All right, so both internal energy and enthalpy only depends on the temperature of your ideal gas mixture. And with that in hand, you can write out some of the partial derivative relationships. For example, if we're looking at the partial derivative of U over V at constant T. Now, at constant T, your U will remain unchanged. It's going to stay constant. So this partial derivative will become 0. And likewise, you can write that version for enthalpy. You have delta H over P at constant T equals to 0. Or over delta V. It's just like the take-home message here is for ideal gases, your internal energy and enthalpy are only dependent on temperature. All right, so 2 take-home messages when we're talking about internal ideal gases. It's the ideal gas law, CV equals nRT, and then your internal energy and enthalpy are only dependent on temperature. So with that in hand, we can work out some of the things that we did last class. And well, last class we derived the general relationship between your heat capacities, CV and CP. So we can work it out for the ideal gas specifically. Now, when we're looking at the heat capacities, CV and CP, I put down the definition here. The CV, by definition, is a partial derivative of internal energy over temperature at constant volume. Or in this case, because we know UT, or internal energy, is only a function of T, it's independent from V, then we have du over dt. So now you see we have 3 different expressions for the heat capacity, and know when to use it is very important. So the fundamental definition of my heat capacity is here, right? So these 2 are our fundamental definition for heat capacity, like Cp equals to dQp over dt, and Cv equals to dQb over dt. So those 2 are just generally true. It's by definition correct. And then if we are considering like a closed system with reversible PV work only, then we can generalize that relationship, not generalize, we can specify that relationship to be the partial derivative of H over T at constant P equals to Cp, partial derivative of internal energy over T at constant V equals to Cv. All right, so this one is the most general. This one is the second most general, or specify it to a specific system where only reversible PV work is taking place. And then here, we're taking one more step to specify my gas is ideal gas. And then this partial derivative becomes a normal derivative of du over dt. All right, so with me so far? So that's why this class, you need to follow a little bit more carefully, just because like this du over dt, this will not be applicable if we're talking about real gas, or if we're talking about a liquid, then this equation doesn't apply anymore. So keep in mind what is the system of interest and what equation to use. All right, nevertheless, so for ideal gases, we have Cv equals to du over dt. For ideal gases in a closed system where only PV work is doing. And we can move terms around to have du equals to Cv dt for perfect gas. all right? Likewise, we can do the same thing for the Cp, which is the heat capacity at constant pressure. So that equals to the partial derivative of enthalpy over temperature at constant pressure. But because we know H is independent from pressure, we have dH over dt. And here is why it's independent from pressure, just another layer of proof, right? So H by definition equals to U plus PV. And for ideal gases, your PV equals to nRT. So in here, we have U is only a function of T, and H is U plus nRT, which is also only a function of T. And we can also rewrite this relationship to dH equals to Cp dt under the same relationship. Okay? And now let's try just work out the relationship between Cp and Cv given all this information. I'll give you like 3 minutes to work on it, and I'm gonna write my equation here as well. So what we're trying to find is Cp minus Cv. So try it yourself. Yes. So the way to work on it is, well, first of all, we ask ourselves, what is an expression for my Cp and Cv? And we work that out from the definition and also from the ideal gas law. So we have Cv equals to du over dt, Cp equals to dH over dt, right? So we're just moving those terms down here. And by definition, we know H equals to U plus nRT, and we can write that into our derivative. And you take derivative of these terms, you find out the du over dt term will cancel out. So effectively, the difference between Cp and Cv for an ideal gas is just nR. So one of the things you can instantaneously grasp is for ideal gases, your isobaric heat capacity, or Cp, will always be larger than your isochoric Cv heat capacity by nR. So that difference is known. All right. And now that's a heat capacity part for ideal gas. And now let's look at the first law of thermodynamics and ideal gases. So recall what our first law of thermodynamics tells you is du equals to dq plus dw. Or if we're considering a specific process, in here we're talking about ideal gas. And we have a reversible process. Now, what we know using these two relationships, if it is an ideal gas, what we know is we have du equals to Cv dt. All right, that's what we just showed for ideal gases, for reversible process, PV work, and closed system. And for that reversible process, we have dW reversible equals to negative PdV. Or in the other word, what we can put is du equals to Cv dt equals to dq minus PdV. And note here, we can use this relationship, the dW reversible equals to negative PdV, only if we specify that process as a reversible process. A different way to calculate for the work is, again, taking the area below that PV curve. So there are different ways to do it, but we're talking about the same thing. We're just taking the integral for that dW. So let's work on an example problem together and see how we can use the first law of thermodynamics and also all these definitions for heat capacities to solve for what is the heat, what is the work that's being done, and what's the internal energy change for a specific system. So this is a specific system we have in mind. That's your example 2.4 in your textbook. We won't go very slowly on this example with you together, because this is a simplistic cycle you can imagine, and we will come back and talk about more of the cyclic process when we start talking about heat engine. So let's read this question together and see how do we approach this kind of problem. Now, reading it, we have 0.1 mole of perfect gas. So now we know it is a perfect gas. So we have this information of perfect gas, and we can write two things, right? So PV equals to nRT, and we know U is a function of T, H is a function of T, and also your Cp minus Cv equals to nR. So that's what we just derived. That's a relationship between your heat capacities. Or what we have is CPM, or molar heat capacities, CVM equals to R. So that molar heat capacity is just the heat capacity divided by the number of moles, just to simplify it. Or in this case, the question gives us CVM equals to 1.5 R. So we can write CVM equals to 1.50 R. And CPM, well, that equals to 2.5 R. And it also specified that your CV is independent of temperature. So that means we can treat our heat capacity as a constant for this problem. Normally, you can't make that assumption because your CV and CP will be functions for temperature, but this question tells you, okay, you can assume them to be constant. All right, the next one we know, it asks for, it tells you that this perfect gas undergoes a reversible cyclic process. So this reversible tells you we can use our dW reversible equals to negative PdV. And a cyclic process tells you your initial state equals to final state. Or for a state function like internal energy or your enthalpy, the change will equals to 0. All right, so these are the things we can get by just reading the problem and putting down what are the equations that might be relevant for us to solve this problem. It might also be useful if you can write down what is needed. So calculate Q, W, and delta U for each step and for the complete cycle. Right, so it's asking you to calculate heat, work, and change of internal energy for each of the steps. All right, so if you don't have a copy of the problem set on your iPad, please take a picture because we will be keep moving on it and I can't keep coming back to the slides. Yes?
Whenever there's a perfect gas problem, will it always specify it's a perfect gas problem?
Yes. We will specify what kind of gas it is.
Okay.
Whether it's, well, yeah, so ideal gas and perfect gas are pretty interchangeable terms. I'm just following the nomenclature in your textbook so you're not getting confused.
Okay.
But ideal gas and perfect gas are interchangeable. We will also specify whether you have like a Van der Waals gas, and we'll give you the Van der Waals equation for that application. Occasionally, your textbook problem do not specifically specify it to be ideal gas or perfect gas, but yeah, depending on if it's talking about the ideal gas chapter, then it's likely to be an ideal gas. I will always specify it in my test and problems. All right, so let's get started by looking at each of the steps and also the entire process. Again, what we want to find is what is the Q, what is the W, what is the change of internal energy. So let's start from our step one. Wait, actually, let me put that cycle on the board. So that's our PV diagram. That's V in Cn minus 3. That's P in, you can start working on it if you like. I'm just for your reference to start. 1, 2, 3. And at our point 1, that's 1,000. 1 ATM. At our point 2, 3 ATM. Okay, so our first step is looking at the process between state 1 to state 2. From 1 to 2. Again, there are different ways to do it, but what I like to do is just write out what are the relationships for these processes. For example, your V1 equals to V2, so it's a isochloric process or a constant volume process, equals to 1,000 cm cert. And we have P1 equals to 1.00 ATM, P2 equals to 3.00 ATM. Now, again, what we want to get is work, heat, and delta U. So for this process, some of them are pretty straightforward. For example, your work reversible for the 1 to 2 process equals to the integral of negative PdV. But in this case, the volume is not changing, so obviously this term is 0 because your V1 equals to V2. All right. You can also calculate your heat. So Q, 1 to 2. So our heat, by definition, you get that by taking the CV over dt from T1 to T2. All right, so this is the definition equation we're using. So your dq will always equal to CV dt. And taking that integral, what we end up having is CV equals to 1.50 nR times T2 minus T1. And in here, we know it's our ideal gas. So you can write T as a function of P and V. So what we have is 1.50 NR times P2V2 over NR minus P1V1 over NR. You can plug in the number yourself and convert the unit, and eventually you'll get a result of 3,000 ATM centimeter. Or if you want to write it in SI units, that's 304 joule. So both of them are correct, they're just different units. In my problem set, I'll tend to specify, like put it in SI units. So that means convert your unit into joule. Yes?
So can you just throw in the N to do, you can't do this?
Well, N is
CVM?
canceled out.
Because if you did CVM, could you just do 1.5 R?
Yeah, that's also fine. Like if you're using the molar heat capacity, then here you have to use the molar volume.
Where?
In here.
Oh, okay.
Yeah, so now this one, the volume is the extensive property. Your heat capacity is also an extensive property. So like if you're using the molar heat capacity, make sure you're using the molar volume and like molar internal energy, et cetera, et cetera. If you're using the normal heat capacity, just use the normal volume, yeah, and so on. Just keep it consistent. All right. And at the end, now we have our W, we have our Q, we can find our delta U. So delta U equals to W plus Q, and that just equals to 304 joule. And let me specify it. It's a delta U for the process 1 to 2. All right. So that's our first step. And let's move on to look at our second step. The logic is the same, right? So our second step, we're talking about the state from 2 to 3. So that's from here, where your pressure is kept the same at 3 ATM, and we're expanding the volume from 1,000 cm third to 2,000 cm third. So this process is a isobaric process or constant pressure process. So for a isobaric process, naturally you should be using the isobaric heat capacity or CP. And we have previously find it out CP equals 2.5 NR. All right, and for this process, we have P2 equals to P3 equals to 3.00 ATM. Your V2 equals to 1,000. V3 equals to 2,000 centimeter cube. So now let's do the calculation together. Let's work on the work first. So work reversible for 2 to 3. That gives you the negative PDV between V3, V2. Well, our pressure is constant at 3.00 ATM times V2 minus V1, V3 minus V2. And that gives you negative 3,000 ATM cm cube, or negative 304 joule. All right, you can do it by taking the integral. You can also do it by taking the area below. So if we're talking about the area below, that's actually also pretty straightforward. We're just trying to find the area of this rectangular, right? It's the same as like you have bottom times the height, which is 3 times 1,000. So it's the same, it gives you the same answer. So that's the work. And then let's look at the heat. So Q, 2 to 3. And that's, again, your heat is by definition given here. Right, so we'll find the QP, which is Cp dt, taking the integral on both ends. We have T2, T3, Cp dt. Now Cp equals 2.5 nR. Change of temperature is T3 minus T2. And using our ideal gas law, we have 2.5 nR, P3 V3 nR minus P2 V2 nR. You can do the calculation and find out it to be 760 joule. And some of the terms can cancel out, right? Yes.
Can you always give us like perfect shapes?
Yes and no. It might be a triangle, right? So it's going to be something that you can easily find the area.
Okay.
Yeah.
In this case, for the finding E, are we using CP instead because pressure is being kept constant?
That's correct. I mean, that's why we're using CP here, because our pressure is constant. Again, when we're looking at this process, that's why I write out what is happening in this process between state 2 to state 3. Right? We specify it, okay, P2 equals to P3, it's isobaric, it's constant pressure, and that's why we're using CP. All right, and if we keep going, we have delta U from 2 to 3 equals to W reversible from 2 to 3 plus Q 2 to 3, and that gives you 456 joule. All right. And some of you might ask, like, because we have ideal gases and we have our relationship of du equals to Cv dt, can you calculate this delta U 2, 3 using the Cv dt? And the answer is yes. I mean, you can try it out and see if you get the same answer. So that's a nice thing about thermodynamics, about this class, is you can always check your answer just using different ways to approach the same problem. So you know you get it right, or you know you get it wrong somewhere. All right, and then let's move on from 3 to 4. So this one, I'm gonna start to ask you questions. What is kept constant for this process? Volume, right? So what's the name for a constant volume process? Isochoric. You can write out V3 equals to V4 equals to 2000 cm cubed. We have P3 equals 3.0 atm. P4 equals to 1.00 atm. And then we have W reversible from 3 to 4. It's an isochoric process, so naturally it equals to 0 because your volume is not changing. You can calculate Q, 3 to 4. That gives you T3, T4, Cv dt, which equals to 1.50 nR times T4 minus T3. And you calculate T4, T3 using the PV equals to over nR. All right, I'll skip doing the calculations, but you'll find out that equals to negative 608 joule. And our delta U of 3 to 4 just equals to Q 3 to 4, which equals to negative 608 joule. And again, keep in mind, what are the physical meaning of heat and work, right? If we're talking about our ideal gas here being the system, then heat is telling you whether you have heat flow into the system, or the system you have heat flow outside to the surroundings. And whether it's positive or negative matters in the process. Yes.
Why is it that if we're going from the same amount of pressure and volume, but on the other side, there's such a large difference in the final?
Oh, let's do the calculations. Yeah, that's a problem. That's why I shouldn't.
I understand the calculation.
No, I know, but if you work that out, you have the different pressure here. You have P4 V4 over an R minus P3 V3 over an R. Now, NR will cancel out. So what is our P4 V4? P4 V4, that's 6,000. Wait, and my P3 V3 is 6,000. All right, so the difference here is 4,000. It's like 4,000 ATM. And this one is very different from what we had before. If you keep in mind what we had before, that's only 3,000. All right. And I have a feeling I made a typo in my actual answer key. I'll fix it later on. All right, and let's work out to our last step, which is our 4 to 1. Now we're going back from 4 to 1 here. And this one is isobaric or constant pressure process. You have P4 equals to P1 equals to 1 ATM. V4 equals to 2,000. V1 equals to 1,000. And we can do the calculation of W reversible 4 to 1 between V4, V1. Again, whatever on the top of your integral, that's your final state. On the bottom, that's your initial state. Negative PdV, that gives you negative 1.00 ATM times final minus initial, which is 1,000 minus 2,000. And that gives you eventually 1,000 ATM per centimeter, or 101 joule. All right. And we can do the calculation for our Q 4 to 1 by using T1, T4, Cp dt. Now your Cp at constant pressure is 1.50 nR. Your change of temperature given by the ideal gas law is P1V1 over nR minus P4V4 over nR. And we end up getting 2.50 times 1,000 minus 2,000 ATM cm cube. That gives you negative 253 joule. Yes.
And in this question, where was CP given?
Well, if you keep in mind, we're talking about ideal gases, right? So we did the derivation at the beginning of the class for the relationship between CP and CV. So CV is not given, but we know for ideal gases, CP minus CV equals to NR. That's how we get our CP from.
Thank you.
And at the last step, we calculate for delta U, 4 to 1, to be, well, 101 joule minus 253 joule. That gives you negative 152 joule. All right. And here comes the nice parts of thermodynamics. What I said is you can always check your answer. So this case, we have delta U cyclic. You can check your answer for this process because we know this being a cyclic process, your initial state and final state is the same. Your delta U cyclic must equal to 0. So in our calculation, what we have, I'm just going to copy paste down. From 1 to 2, that's what we have. From 2 to 3, straight to 4, and from 4 to 1. All right, if we add all these numbers together, we have 304 plus 456 minus 608 minus 152. And that also gives you 0. All right? So the nice thing about thermodynamics is you can check your answer and make sure it is correct. Okay, how do you feel about this problem? Okay, so again, what we're doing here is we introduce lots of abstract concepts. And I really don't want anybody to be frightened by these partial derivatives and equations and integrals and calculus. So just really think about it. What the problem is asking, what equation I can use, and how do I solve that problem? Okay. And let's move on to talk about a special case, which is an isothermal expansion of gases. So this one is a little bit of an extra that I want to use this as an example to emphasize the difference between heat and temperature. So we mentioned a lot when we're talking about heat. We're talking about the heat that's being transferred from the system and the surrounding, or vice versa. Now, heat is deeply related to temperature, but it's not the same as temperature. So in this case, if we're looking at an isothermal expansion of gases, imagine what we have is your temperature is held the same. And by changing the volume and pressure of your gas, you end up getting a different combination of your volume and pressure. Now, their product might be the same, but the temperature is held the same at all time, but your volume and pressure might be changing. Now, will heat be 0 for this process? And the answer is no. And let's work out what is the heat for this isothermal expansion of gases or contraction of gases. Now, imagine what we have here as initial state. You have it at some V initial, P initial, at some temperature T. And at the final state, we end up having V final, P final, and temperature. The temperature remains the same at all time. Now, in this process, in order to understand how things are going, we want to introduce a hypothetical state. What that hypothetical state means is, let's assume the first transformation is an adiabatic process where your heat transfer is 0. There's no heat input. Now, in this case, we're talking about an expansion for your gas. So your V final will be larger than your V initial. Now, in that process of getting from your initial state to your hypothetical state, your total energy must be conserved. And since we know U equals to Q plus W, and in this case, the system is doing work on the surrounding, so the temperature must drop. All right? It's just from that hypothetical state. And then from here, from VF, what we have is then we keep that volume fixed. That's after expansion, after the adiabatic expansion of the gas. And you have the pressure change and your temperature returns to its initial temperature via some kind of heat input. Okay, so let's look at the equations, it might be easier. So let's assume it is an ideal gas. So we have PV equals to nRT. So for this process, where we have a reversible expansion, the reversible isothermal expansion of your ideal gases, we have W reversible equals to negative PdV. Or we know it's ideal gas, so we have P equals to nRT over V. We plug it in. We have nRT over V for V final over V initial dV. Now your N, R, and temperature are all constant for this isothermal expansion of gases. So we can take that out to be nRT V initial to V final 1 over V dV. All right, so when we're doing this calculation, you take that integral, you end up getting negative nRT ln V final over V initial. So the process involves some kind of work between your system and the surroundings in your isothermal expansion of gases. Now, if we look at the positive or negative, we have V final larger than V initial for an expansion. So your work reversible is a positive number. It's a negative number, sorry. Right, because we have this negative in front. So what it means is your system is doing work to the surroundings. So your work is a negative number. And then because we know for ideal gases, when delta T equals to 0, you have delta U equals to 0. So the total internal energy is not changing for this isothermal process because the temperature is not changing. As a result, we have Q equals to delta U minus W, and that gives you an RT ln V final over V initial. Or the other way to put it is your Q is a positive number for this expansion. Or the other way to think about it is for this isothermal expansion, even if your temperature is not changing, the heat flow is not 0. All right, so heat and temperature, they're deeply related. But when there is no temperature change, it doesn't necessarily mean your heat will remain the same. Yes?
So this one, we say the change in temperature is 0, so the internal energy is 0 because it's an ideal gas?
Yes.
Okay.
Yeah.
When you say temperature is the temperature of the system.
Yes.
Does enthalpy apply in this situation?
It depends. Well, we are not working on enthalpy for this specific process because enthalpy should still remain the same because the temperatures remain the same. But I don't know how enthalpy is going to come to play when we're talking about heat and work. It becomes more complicated. All right. Okay. I think I'm running out of time, but next lecture we will run over more examples in how do we understand different thermodynamic process with perfect gases. And if you print it out, just keep it with you for our next lecture.